Let's do it the easy way. Might be able to do this, so I get to see. Okay, for the chat. Yes. Is this good? Is this the proper size?
Yes. It's now in full screen and it's full size.
And I did an early. It's perfect.
Yes, about 7 minutes. Thank you for coming early for the setup.
Oh, thanks for the invitation.
Thank you. I think we can start on time and people will come one by one. That's fine.
Cool. So are you recording already?
Yes, yes. I'm recording and we're streaming on the YouTube.
Okay, cool.
Yeah, so welcome everyone. We are very excited to have Professor Machado with us today for your wonderful talk. Professor Machado, the stage is yours and we're very excited to have you.
Thank you. Thank you so much for the invitation. So today I'm going to be talking about representation-driven option discovery reinforcement learning. So this is a mouthful of a title, but it is a talk that I've given a couple of times already. But the reason that I chose to give this talk is because in the spirit of being a guest lecturer for the Parallel course, I think that it touches upon a lot of interesting topics that are just relevant to RL in general. And more than that, it's also because as I was looking at the list of invited speakers, the other guest speakers for the course, I realized that also it cuts across a lot of the things that they talked about. So I thought it would be a good way of like trying to put a lot of this together. Okay, so this is a somewhat of a different talk because what I'm going to be doing today is to talk about this from the perspective of a research program. So I'm not going to come here and say, hey, look, this is one paper and this is another paper, and let me tell you about the results of the paper. Because, I mean, I will, of course, talk about papers, but it's because I think that, in a sense, the interesting part for the pedagogical purpose of a course is, in a sense, show you a path, like how we start from a very simple idea and how we can bootstrap from that idea and keep getting more and more success. And then you can just see the journey of how we got to that point. So, of course, I will talk about results and I will have papers, the reference at the bottom for you if you want to follow up, but it's not going to be necessarily focused on a single paper or on a few papers, but many papers telling a story. Okay, and I did my best. Hopefully, I didn't drop the ball to make sure that every time that a student was involved in was leading the project, I let their picture in my slide. Okay, and as I said before, this is a research program that touches upon a lot of what you've seen in the other guest lectures. So I think it's always interesting to see the serendipity of those different researchers and how a lot of what we're talking overlaps with each other. Okay. Um, Now, I don't need to start telling you about reinforcement learning and how there's an agent interact with the environment, or even what deep reinforcement learning is, which is used for neural networks for functional approximation. I don't need slides for that. After all, this is a deep RL course. But the thing that I want to start emphasizing here is that, well, RL now is commonly deployed in the real world, right? Like we go from video games that are more than 10 years, video game results that are older than 10 years at this point, to being able to fly balloons in the stratosphere, actually provide internet to people for a longer period of time, to being able to control the plasma inside the nuclear fusion reactor, getting a configuration that people even were not even sure that it was possible. So RL now is full of success stories, and in a sense, that's exactly why we have courses like the RL course. And of course, what I'm saying here is just these are some of the nature papers that were published that you can get nice visuals for, but there is way more, right, about this. And these slides are this particular slide is even outdated because I'm not talking about RLHF, for example, and all the impact that reinforcement learning has been having on LLMs. But all this is to establish that, yes, we can do this, and we have been doing it really well. Now, it begs the question, if we have so many successes, and if this is, and if we're able to consistently get these results, what's left to do? Like, are we done? What is that we need to be able to answer? And now it's a matter of taste, right? But I think that we're still somewhat limited in terms of the how far ahead we can plan, how complex the sequence of tasks that we need to be able to accomplish are, and And in a sense, I think that what we're actually missing here is a better notion of temporal abstraction. And what I mean by that is that when we talk about reinforcement learning, right? We say, hey, we have an agent interacting with the environment at each time step. So we have this, let's say that this is a state here. At every time step, the clock ticks and you're in a different state. And then you have to select an action. And then you are in a different state. And then you have to select an action. But if I were to ask you, like, how do you make coffee? Make coffee for me. You are not going to be thinking about, well, I need to move my hand a little bit, and then I have to twitch this muscle a little bit. And you're not going to be doing this at a millisecond by millisecond. What you're going to do is to say, well, maybe I should get a kettle. And then I should fill it up with water. And then I should boil that water. And then I should put the powder on the filter while I'm boiling the water and stuff like that. So the thing that's interesting is like, well, maybe I should grab a kettle. And maybe I should fill it with water. And maybe I should boil the water. If you notice, like we have these very abstract actions, and the key thing here is that they don't take the same amount of time, right? We have actions that can be very fast, like grab the kettle, but we can also have actions that are very slow, which are maybe, I don't know, if you want to bake a cake and wait for 8 hours, you know. So how can, in reinforcement learning, we get this notion of temporal abstraction? How can we expect how can we tell the agent that, hey, instead of thinking about it at each time step, you should be able to think about that a temporally extended interval of time, you know? And I still think that this is a fundamental question that prevents us from tackling more complex tasks. And it's just something that we humans naturally do, you know? There is a way to do this. This is a paper that was written a long time ago by Rich Sutton was one of the authors, Leonard Prickup, Satinder Singh. So Rich was one of your guest speakers, right? And the idea here is that there is this notion of options, and options are going to be a formalism that's going to allow us to leverage the reinforcement learning machinery for this extended sequence of this courses of actions, you know. In practice, the way that it's somewhat convenient to talk about options, it's not the most general one, but for the purpose of this talk, it's appropriate, is to think about that as a subroutine. You know, like if you're, let's say, you're writing code, you don't write a single file that has line by line all the instructions that you're going to follow, right? So sometimes you call a function that says, well, sort this. And now when you call that function is going to go off and do its thing. And then when it returns, you know that the list that you gave it sorted, right? So in a sense, it's very similar to how we can think about this notion. We're just like, we can give up the autonomy for a while to be able to accomplish this on a different level of abstraction. But of course, the agent is the one doing everything. In practice, the way we formalize this is that we're going to say that an option, omega, is a tuple that has an initiation set, a policy, and a termination condition. What does it mean is the following. The initiation set is going to be the set of states in which that option is available. If I want to boil the water, well, I might as well be in front of the water first, right? Otherwise, there is no point for even trying to boil the water. If we want... But then once we decide to do this, what is the policy that we follow? What is the actual actions that we take? But then also, when do we know that we're done? You know, and this is what options do. And the thing is that they're nearly not as popular as, in a sense, they should be, because we use these temporal abstractions all the time in reinforcement learning. But they work, and they have many use cases. You know, they were originally introduced with this notion of faster credit assignment. If after I do all these steps and I have my coffee, I think that it's not good, it's much easier for me to assign blame, let's put it this way, to say that, well, maybe the water was not hot enough, so maybe my option of boiling the water was not the effective one, instead of thinking that, well, maybe 30 seconds ago, I twitched my muscle a little bit wrong. Like that's not how we can assign credit. And it's not the right level of abstraction for us to think about the outcome of our actions. We can also, options also afford us to do better exploration, because, and this is a topic that, I don't know, Ian Osborne talked with you about, that Ben Van Roy talked with you about, which is that a lot of the problems with exploration, and I suspect that Ian talked with you about this, is this dithering, right? Like this back and forth, keep going back and forth, and you're just wasting too much time trying to do this. There is a reason for us to do this, in a sense, because you have to make some assumptions. But if you want to, but for a lot of environments that have some structure, what you really want to be able to do is to have this purposeful behavior. So if I say that, oh, I want to try to, I don't know, boil water, there is no point for me to be like going back and forth, go back and forth. I should do that action for an extended period of time to see the consequence. And the example that I like to give is if I told you that, hey, I hid $1 million somewhere on the university campus, you wouldn't be going back and forth, trying to bump into that money, right? Like you would say, well, let me try that building, and let me try that building, and then once you're in the building, let me try that room and that other room. So again, you have this hierarchy of behavior, and then finally, another thing that we can talk about is transfer learning, because again, let's say that you already know how to make coffee, and you have all these skills that are required, like, I don't know, boiling water, grabbing the kettle, and stuff like that. The moment that I ask you to, hey, can you make tea? Maybe you've never made tea before, but you have a couple of skills that are reusable in that environment, and that would allow you to solve more tasks, because you can compose them, you can combine them. Okay, so there are many use cases for options, and they work. Like an example that I really like, in a sense, I'm very biased because I'm an author of this paper that we published at Nature. But when we were trying to design a controller to fly balloons in the stratosphere, basically the balloons had to go, like the actions that the balloons had was to go up or down. So you go up or down for 3 minutes, and of course, taking those actions actually costs energy for the balloon as well. So if you would just let the balloon deter for a very long time, it would run out of energy, even before it was able to, by chance, do a random walk up to a different location. So instead, the strategies that the balloon had when the balloon decided to explore was to come and say, well, I'm at 15 kilometers and I want to explore 3 kilometers above me. So the balloon would take the actions for an extended period of time up to the point that it was at the 18-kilometer altitude. And now, let's say the balloon is there, and then the balloon decides that, you know what, I want to explore again, but now I just want to go 300 meters below me. Now, the balloon would take the sequence actions that would lower it by 300 meters, but notice that traversing 3 kilometers is very different than going down 300 meters, like in terms of duration of actions and so on. So the balloon, when the balloon was doing exploration, the balloon was deciding which altitude to explore, and then it was just executing this extended sequence of actions, and this just works, and this was actually one of the key elements to get the solution to work. So we do have evidence about this. But now there is a catch. The catch is that it's very hard for me to give a talk talking about the high dimensionality of winds in a 3D voxel to give intuition about how to do things. So we're going to use a much simpler and more pedagogical example, which is this notion of exploring at a higher level of abstraction. Okay. So what we're going to do is that we're going to use this much simpler example, which is this 4-room environment. And the reason we're going to use this, and I'm going to relax this, I'm going to talk about many different environments later on, but it's just because we have this very natural notion of different places that we could go with different abstractions, And what we're going to be focusing on for most of this talk is going to be the problem of exploration, okay? And the analogy that I like to give is, let's say that you are this agent A, and you have to stumble upon this +1 in model-free reinforcement. Well, you can actually do it. We've all coded something like that. You just run a random walk and eventually it stumbles upon this +1. The catch, though, is that quite often we don't actually watch the random walk. Our computers are very fast. We hit run, and then look, it already hundreds of episodes have executed even before we can pay attention to what's going on. The problem, though, is that if you actually look at the number of steps that we need to be able to use this plus one, we're talking about the orders of thousands of steps. And look, it's kind of weird because it's a 10 by 10 grid, and somehow we're okay spending thousands and thousands of steps into just stumbling upon this thing. Because what we're doing is just say, well, I'm going to maybe go up or down, left and right, and I'll just keep sampling those actions. But what if instead of doing that, what you actually did was to say, you know what, I want to go to one room, and then to the other room, and then to the other room. If you have this high-level action, so let's put it this way, you would then be able to explore the environment much more effectively. In fact, you reduce that by an order of magnitude, the number of actions that you need to take, okay? The problem, though, is that the example that I gave you before about the balloons, or this example, I'm giving you the abstractions, right? Like I'm telling you that, hey, look, the altitudes is the right abstraction, or the rooms in this case are the right abstractions. And what I really want to do, like the question that keeps me awake at night, is just this question about how do we come up with those abstractions? You know, like by just a very experiential way, similar to what maybe you heard from Rich Sutton in his talk, just thinking about the agent sensory data stream and the experience that the agent has. How can, by that sensory data stream, the agent can come up with abstractions that make sense? You know, like, or more informally, where do these options come from? And this is the question that I want to ask, you know? And to be able to formalize this question a little bit, I'm going to start introducing some notation, okay? So this is a general value function. And the idea here is that this is a generalization of the concept of a value function to things that are different than the reward, okay? So what we're going to do is that we're going to try to make predictions of signals, and we're going to call the signal C, cumulant. And we're going to make predictions about the discounted sum of those cumulants, okay? But we're going to do that for a specific period of time. It's not going to be until the dead hit of the universe, as we generally do with value functions. So we're going to add a stopping value. So the moment that you stop making that prediction, you're also going to get a value. And now what we're going to try to predict is, well, how much am I going to accumulate along the time, plus what am I going to get at the moment that I decide to stop making this prediction, okay? And the way that options are defined is going to be options that are defined as a way of trying to maximize the C, okay? The reason that this is interesting is because this is a very elegant way of modeling the option discovery problem, which quite often people just talk about it in very loose terms. But then here we can basically come up with a unified view that pretty much explains everything that you've seen out there, you know? What we're going to do is that we're going to define a problem for the option to maximize, to solve. And the problem that the option is going to solve is to maximize the discounted sum of cumulants plus the stopping value. So C and Z, superscript here, they define the problem that we want to solve, you know? And at the bottom, it defines the solution, which is the policy and a stopping function. So K here is going to be a random variable because it's going to be when the option terminates. And then what we're going to do is that we're just going to learn a policy that maximizes that, including termination, okay? So if you think about that, what we're saying here is that in this very simple equation, if we commit to this formalism, we're not necessarily giving up anything in terms of expressibility or expressiveness. But if we commit to this formalism, what we're saying is just like, we can write both the option discovery problem and the solution itself this way. Now, the question about where options come from end up becoming just a question about how do I define those subtasks, you know? So let me give an example about this. Like now, to define the option, we just have to specify the subtask that the option needs to solve. And the canonical example are shortest path options to bottleneck states. You know, like, so this is what everyone presents. Every time that you see the four rooms, people are trying to say, oh, well, can I find those four corners, those four doors in the four rooms? And those would be the options. And then we can define those options that way by just defining the cumulant to be -1 at each time step, 0, and then when the option terminates, it gets 0 at the subway states, or -infinity otherwise. So if it gets -infinity otherwise, we want to make sure that it never terminates there. So all we are saying is just like, hey, go as fast as you can because you're accumulating negative reward to the go state, to this bottleneck state, and then once you're there, you terminate, and then you end. You know, and that's one way that we can talk about options. And what's nice about this is, again, it gives us a single algorithm formalism to talk about, well, this is how we instantiate each one of those elements here, instead of the thousands of different ways that people present the algorithms, but at the end of the day, this is what they're doing, okay? So now we can refine the question, the research question that we're going to be discussing this talk, and it's going to not be where should options come from, but what subtasks should we be using, you know, like using this JVF formalism. And the answer, and what I'm going to be talking about, is the title of this talk is this notion of representation-driven option discovery, okay? The intuition is very simple. We're going to have an agent interacting with the environment. At first, the agent doesn't know anything, so we can think about maybe the agent taking random actions, or maybe the agent is given a data set. I'm really agnostic to this. The agent is going to interact with the environment. But from the data that the agent is going to collect, the agent is going to learn a representation, okay? This representation that the agent is going to learn from its interactions with the environment, they are going to be used to generate a subtask. So the subtask that we're going to pose is going to be a function of the representation that the agent has learned. And then when the agent solves the subtask, the agent is then going to learn an option. By learning this option, the agent is now going to have, remember, a skill. Imagine that before you didn't have the sorting function available to you, now you do. That empowers you to do things that you couldn't otherwise do. Now, because you can do things that you couldn't otherwise do, what happens is that when you interact with the environment again, you're going to be getting different types of samples than you would before, because you are empowered by skills that you didn't have before. This is going to change the data stream. You're going to then learn representations out of that again. You're going to learn more skills, and then you keep going in the cycle. You know. And what's nice about this is that if you look at this, this is a very constructive cycle. We're actually building from from the previous iteration to bootstrap of the behavior and generate increasingly complex behavior out of this. You know, the cheesy example that I like to give about this is this result that it's this well-documented phenomenon that when children, toddlers, are learning how to walk and to speak, when toddlers learn how to walk, you observe an explosion in the vocabulary that they have. And psychologists are better scientists. They are not necessarily going to attribute causation to that. But the way that I like to think about that is to say that, well, maybe what's going on is that the fact that this toddler learned how to walk allows the toddler to interact with things that it wouldn't be able to interact before. And by interacting with these things, it's experiencing things that it had never experienced before, which forces it to learn or represent learning words to things like I don't know, an outlet. You generally don't use that word on a daily basis, but the moment that you have a toddler trying to stick their finger there, you will call that word. That leads to new words that are learned, and these new words and that allows us to learn those new things. So the real question is, how do we instantiate each one of those things? And remember, I told you that we're going to do this for exploration. So the idea here is that, let's say that we're going to do a random walk. This is the let's say that we can visit some portion of the state space given how long we're willing to wait. But now what we're going to do in terms of subtasks is that we're going to pose a subtask that says, I want you to go to a place that you can get to, but it's hard to get. So the option is going to then take you to the frontier of your knowledge there, the frontier of the place that you've been. And now, when you are empowered by that skill, when you have to interact with the world again, it's relatively easy for you. You're one option away from just ending up at the frontier. So which means is that now when you do a random walk, you're much more likely to keep pushing the frontier, and then we can bootstrap off that. And we have demonstrated this in many different settings. This is the pinball environment, for example, where basically you control a ball here, and then you have to take actions to bounce the ball around. And if you do a random walk, again, what you can see is that, well, it's really hard to go through these regions because of how the environment is structured. So because of that, what we're going to do is that we're going to spend a lot of time here. But now when we apply this framework, what we're going to do is that we learn this option that bounces around, but eventually ends up here. And the reason that it ended up here is that not that it has any particular semantics to this place, except that this is a place that the agent knows it can get to because it has been here before, but it feels very hard because from the agent's perspective, the agent hasn't been here much. But now the moment that you're empowered by this skill, you get the ability to just go through this region. And it's much more likely that now a random walk is going to cover that part of the state space. Okay, and then we can keep refining over and over again. So back to this cycle here, the real question is, how do we instantiate this? How do we make sure that, how do we actually come up with algorithms from this very high level perspective? And the answer is going to be, we are going to use something that it's called the success representation. We're going to start from something that it's called the success representation. By this point, I guess you heard a lot about it in this series of lectures, because I think that Ida talked about this with you, Ben Eisenbach, I think that he talked about this with you. And this is just a notion of predictive knowledge that I suspect that Rick Sutton talked with you about. But the idea of the success representation here, which was, of course, introduced by Peter Dayan, who also gave one of the guest lectures here, the idea of the success representation is that it is going to be, it is trying to capture the notion of similarity over time, not over space or observations, And again, maybe you can draw the connection by just this notion of trying to keep going back to the notion of time here, for both the temporal abstractions and this. And the idea here is that in supervised learning in general, let's say we look at two images. And if those images look very similar to each other, they're very likely to be very close in an embedding space. They're very close in value, right? But now imagine that these two images, they lead to very different outcomes over time. Now, in that sense, in supervised learning, it doesn't really matter because we're just thinking about one step, but this does matter in reinforcement learning, right? So the example that I like to give is, imagine that you have this state A and this state C here, okay? Now, from a simple perspective, well, if you were to look at the XY distance between these two states, it's actually small, right? Much smaller than when compared to B, for example. Even if you were to look at potentially some observations, well, it's a state that it's surrounded by empty space, but there is one wall beside it, which again is very similar to what we have here. But of course, when you look at this looks fundamentally different, because you know that, well, for you from A to go to C, you have to go around this wall, And this is what the success representation captures, is this notion of temporal distance between things, The way we're going to do this is that it's going to be the discounted sum of future state visitations. So basically what we're doing here is to say that, well, given a particular state, I'm going to have S features, and where S is the number of states in the environment. And each one of the features is going to tell me that how many times do I expect to visit this other state, given that I'm in this state, in the future, discounted. And this is what this equation 1 is showing. We can use, again, the notion of GVFs to formalize this, where the cumulant becomes the indicator function for state visitation. The gamma and the pi are shared across all the cumulants because we're using for the success representation. And then there is no necessarily stopping value. Okay, but the moment that we have this, we can define a success representation. And what is cool about that is that it's capturing this notion of time, but more than that, you'll remember that I was giving you this intuition about I want to go to a place that I know I can get, but that are hard to get. In a sense, I want to get to the sphere of my knowledge, to the place that is further away from where I've been, that it's hard to get. This captures a notion of this has this feeling of a diffusion process. Like if you think about this, think about heat, how heat propagates on a rod or something like that. Well, if you put a fire on one side of the rod, well, the place that it's going to take longer to warm up is going to be on the other end. And there are ways that we can model all this process of diffusion. And then the beauty of this is that once you do the math, we can actually capture these properties of diffusion by looking at the eigenvectors of the success representation matrix. This has been designed in one of the papers that I wrote a while ago, because we draw this inspiration actually from graph drawing results and the Laplacian representation. But the whole thing that we're going to do is that, you remember we have this S by S matrix, which is like basically S rows, which are all the states, and S columns, because it's from each state how many times you expect to visit other state, discounted. So now what we're going to do is that we're going to compute an eigen decomposition of that matrix. We end up with eigenvectors, right? And now and you remember the rod cycle here? We're going to learn the representation. So the representation is going to be the eigenvectors of success representation. And now the subtask that we're going to do is that I want you to be able to traverse in the direction that eigenvector is pointing to. So this, for example, is the eigenvector, the second eigenvector in this four-room environment. So basically, the eigenvector has S states, right? Like, sorry, S dimensions, S is the number of states. And then basically, I'm just plotting here the value that the eigenvector assigns to each one of these states. So what you can see is that clearly there's this direction from here to here. And what we're going to do is to define the subtask that is going to be the dot product between the eigenvector and how much I moved in the space. So, because that's a way of saying, like, well, I want you to traverse in this direction. You know, intuitively speaking, if you think about this in the tabular case, and you represent this as a one-hot encoding, basically you are rewarding the agent by the gain in height from going from one place to the other. So the moment that you gain height, that's the difference that you get is the reward. You know, and then we can define an eigenoption as being the option, the policy that solves, that maximizes the cumulant, and upon termination, it gets no stopping value, and then we can actually, and then the way that we define this is that the moment that you get to the top of this plot, you're done, and then you can call it, okay, and this is captured by this condition here in the So that's it. With this, we can actually instantiate this framework, and we're going to use a random policy at first. We're going to learn a representation that is going to be the eigenvectors of success representation. We're then going to pose a subtask and solve the subtask, and it's going to give us eigenoptions. Again, this is the policy. I didn't emphasize it in the previous slide, but the policy that is just taken to the top of this place here, right? But now we're empowered by this option that we did not have before. So now we're going to empower the agent, and now the agent is going to have access not only to the primitive actions, but to the option that we discovered as well, which the agent can then interact with the world again and keep improving its behavior. You know, let me give an example, because of course, if you're listening carefully to it, there is a catch here, right? Like, because I'm starting from this assumption that I have access to the whole environment, so I can compute this structure. And if I have visited every state, and I know how many times I'm going to visit every state, why do I even have to bother in trying to come up with this for exploration? But clearly, the idea here is not that we're going to do this. I'm giving you this example just because it's clean for you to understand what is the intuition, but we can actually do this in an iterative process. And this is the example that I want to show you. So let's say that we start at the top right corner here, and we're going to take a random walk for 100 steps, okay? After 100 steps, this is the state visitation. I just counted the number of times I've been to each state, okay? So the agent, by chance, has spent a lot of time in this state and not that much time in this region here, and so on, okay? But now I can compute the success representation induced by this data. This is what it looks like. And once I do this, I can actually learn the option. I compute the eigenoption that it's induced by this representation. Now, if you follow the arrows, you're going to see that the eigenoption is terminating here. Why is it terminating here? Not because of the bottleneck. It doesn't even know that the bottleneck exists. The agent has never been here. But it wants to terminate here because it's a region that it has been only one. It's a state that it has been only once in a region that it hasn't visited often. So that feels like an interesting place to go to. But now the agent is empowered by this skill that takes it further. The next time that it does a random walk, it's much more likely that it will end up in the second room. We can update the eigenvectors. We get another option. We can empower that with the agent again, and the agent gets to go to the third room. We do it again, and then the agent ends up in the fourth room. And it's hard to convey how excited I was when I saw these results for the first time, because, again, if you haven't watched the random walk, you actually don't realize how slow it is. And here we were seeing the agent being able to explore the 4 rooms in 400 steps. That's quite something, you know. But of course, this is just one run, it's used for pedagogical purpose, but we can actually measure this in a more quantitative terms. And what we can see here is that we reduce, if we want to compute with this setup that I start from the top right corner and I want to visit every state in the environment, the number of steps that it would be needed for me to visit all states in the environment when the episode length here is 100, it's approximately 27,000. But then when we follow this broad cycle, we reduce that by an order of magnitude. But more than these numbers themselves, another thing that I find it's interesting is that if you look at this is the random walk. You can see that, yes, it's slowly diffusing from the start state, as you would expect. It almost looks like, yes, if you were to measure the temperature, and here is the fire, this is how the temperature would, in a sense, decay. You know, like not necessarily the same rate, but this is how you would expect the gradient of temperature to be. And here it's very different, because we see these patches here, because the agent is being very purposeful in going to the other rooms, because it knows that this is what it allows it to reach other areas, you know, and get much closer to uniform visitation. So this works, you know. There is a catch though, and the catch, of course, is that if you think about this, like, well, I'm going to have a matrix that it's S by S, the number of states doesn't really scale. And even if we could represent this matrix, I still have to pay a cubic cost to do computation. And so can we approximate this? And of course, the answer is that yes, we can approximate this using neural networks. And this is one of the people who did this is one of my PhD students, Diego Gomez. And the idea here is that we're going to have a neural network that is going to receive an observation. It can be whatever you want, XY coordinates, images, whatever. And now what we're going to do here is that we're going to have as outputs to the neural network D nodes, because we want to approximate the top D eigenvectors of the graph Laplace. Okay, so what that means is the following. I'm going to, let's say that I'm in this state. Think about that 4-room environment that I was giving. I say, hey, I'm in this particular state here. You feed that to the neural network, maybe as a one-hot encoding. And what the network is going to give you is like, this is the value of the eigenvector in this particular state for the first, second, third, all the way to the eigenvector. You know, so it's as if every time that you query the neural network, it's going to give you the height of that plot in a particular state. The way we do this is using some graph drawing objective that leverages that equivalence between the success representation and diffusion. And the idea is that we want 2 states that are close in time to have a similar representation. We want to minimize this value. And this is to guarantee orthogonality and smoothness over the objective function. Okay. Other people had done this before. The reason that I'm excited about this particular formulation of the problem is that this approach that we have is more robust, more accurate, and it works across different data streams. And even from a hyperparameter perspective, this is our approach. No matter what hyperparameter we choose, we are consistently converging to the right answer. While other approaches, they were very finicky, and depending on the choice of hyperparameter, you would converge to different locations. Okay, but we are able to do this now. We're able to approximate this, and this allows me to finally get to where I wanted, which is to be able to put all this together. You know, because again, as I said at the beginning of the talk, this is supposed to be a trajectory, and I wanted to show you the intuition and how those things are built, instead of just coming to you and saying that, hey, this is the final algorithm and this is what it is. So you understand the intuition. But of course, this notion of cycles and stuff like that doesn't really, it's kind of too many things to string together. So ideally, we just want to have a single monolithic algorithm that works. But if you look at this diagram here, we have to be able to scale up if we want to do actually deep-RL. Every single step along the way, right? Like the representation learning process itself, we have to learn because we can't just assume that we're going to have one hot encoding or stuff like that to be able to even do things tabular. And that's what I was telling you before about this proximity function, because now we do have a representation that's able to do this. But more than that, we now have this representation, we can then pose the subtask and solve it, and we can use deeprl to solve it because it's just a reward maximization problem now. And then we can come up with a way of incorporating those values into the object such that it empowers the agent so it can do it can interact with the world. Okay. Martin Klisserov, who is another one of my PhD students, has done this. He actually did this before the paper that I showed you, that Diego. So we actually used the previous method that existed to learn the Laplacian representation that was not developed in my group. And then we used double DQN with n-step returns to learn how to maximize this intrinsic reward that is generated, and to also learn how to maximize reward itself, because it's RL. At the end of the day, we still want to maximize reward, right? And notice that you remember that I told you that the reward function that we're going to maximize is just a gain in height. Every time that we take a step, we see how much we moved in height, and that's what we get. Well, guess what? When we query the Laplacian representative, we query this neural network, we literally get the height, right? So all we have to do is, as we interact with the world, we're querying this and it's getting us the height at each time step. So we just take the difference and then we get the reward. So it's pretty straightforward in that sense. And now it's the part that it's maybe a little bit boring, because long story short, it works. It works, and it works really well. It works better than many of the baselines and the standard solutions that people have, such as things like random network, count-based exploration. And in this particular case here, we start at the start state, and we will need to go to this state here, but we're going to feed to the agent images. So now we're not doing one hot encode, we're not doing tabular anymore, we're just doing pixel-based observation, so it's fairly high dimension, okay? The other thing that's happening is that there are no phases here. Everything is happening at the same time, so we're learning everything at the same time, all the networks. And they are combined, and then we're being able to learn that online, okay? So this works. One thing that I think it's fairly interesting is that when we introduce non-stationary, or like not a notion of continual learning, if you need to be learning continually, which is, I believe, maybe Martha White talked with you yesterday about. So let's say that we start here as before, and we want to go to this region here. Well, that makes a lot of sense that we can do well. I just showed you this before, right? Like, this is pretty much the same task as here. It's just a compressed curve. We can, and we are doing really well with this blue curve that it's our thing. But now, let's say that halfway through, you don't know that the world has changed, but the world changes. The agent's not told so. Now the agent starts here, and then the agent needs to go here, and some of the walls are blocked. So now, what do you do? Well, the notion here that it's interesting is that for a lot of these other methods, like count-based exploration, if you're not told that the world has changed, what do you do with your counts? You don't get to reset them. So now you have counts of wrong things, because maybe you should revisit those places and so on. But when we think about this notion of options for exploration, what it allows us to do is that, well, they're just the skills that we acquired. We acquired this skill to go from one room to the other, right? When the world has changed, those skills haven't gone away. In fact, they're still useful. And that's why we teach, undergrad students the basic principles of computer science, and we're not teaching them how to implement things in Java 5.732. It's because, well, those skills that we're teaching students, they generalize. So when the world changes, you get to explore and learn how to do what you need faster. And this is what we're being able to capture here upon these changes, And I think that this is very exciting. We kick all sorts of coders out of this. In this particular example, the agent needs to come here and break the wall, get the key, and leave. The reason that I like this example is because when I talk about, again, the compositions, sometimes people come and say, well, but is this assumption that the world is symmetric? And maybe the world doesn't need to be symmetric, because at the moment that I break a wall, I can't put it back. Like, this action is not even reversible, but we're able to do really well. Maybe you're convinced. Maybe you're excited about this. Maybe you're looking at this like, well, you just have great worlds. You still have great worlds. And this is something that always bothered me in a sense, because people would always say, oh, this is only for navigational tasks. When in a sense, it's not. because any MDP is going to be seen as a graph, and we're traversing that graph from one state to the other. Grid worlds or this examples from Pixar are just convenient ways of depicting that. But we're able to do this in all sorts of other environments, right? Like we can look at this, for example, for Montezuma's Revenge, which is this hard exploration game. So here the agent needs to jump over the rope, go down the stairs, avoid the skull, and get the key. So now the agent can go all the way back and open this door. So what we did was that we let the agent wander in the environment for 1 million steps, taking a random walk, okay? And once the agent has acted in the environment for 1 million steps, we looked at what is the eigenfunctions that we would learn from those transitions. And lighter values are higher. And what we're doing is we're tracking the position of the yellow pixels on the hat of the agent. So, but what you can see here is that, well, the eigenfunctions assign a really large value to getting close to the key. And it makes sense, not because the key has any special semantics. The agent does not know what a key is. The agent is not even looking at the reward that it gets when it gets the key. But what the agent is being able to see is that, well, this is a place that within 1 million steps, it's really hard to get. And this looks like a cool place to go. The second eigenfunction that we get is something that wants the agent to be at the bottom of the stairs, and so on. And what it's interesting is that this is reflected on reward maximization. You know, like in Montezuma's Revenge, for example, within 200 million steps, we're able to learn how to get the key and get to 2500 way faster than any of the other methods. Yes, our ideas is still going up, but again, we haven't run our method long enough as well to see if we could get to the same performance with billions of steps, you know? Looking at 3D environments with partial observability, we also are able to do quite well. And actually, some of those environments are the only thing that we actually get to use to succeed on how to accomplish a task, you know? So all this to say that, like, I think that this is really good. Now there's this question: are we done? Like, I'm telling you that we can have this option discovery method that we're doing really well for exploration, and then there's this question: okay, so what do we do next? Okay, and I think that there are two answers here. Well, I can give you more demonstrations, or I can give you more algorithms. And what do I mean by that? Well, more demonstrations, like maybe you are not convinced by Atari and 3D navigation tasks in grid worlds, and maybe you say, well, what about Mujoko? Or what about, we have results in Mujoko, but like, what about Mujoko? Or what about Minecraft? What about whatever? Or you can kind of say, well, sure, but like, maybe there's something else that's missing, you know? And I want to say that both paths are valid, but I want to point out that learning from scratch, and we're learning from scratch here by on purpose. They're inspired by the perspective of experiential learning that Rich Sutton was talking to you about. It's slow, almost by definition, because we don't get to leverage domain knowledge. And I think that the problem here is that the moment that we do this, we end up being constrained, because by just random exploration, even if it's purposeful random exploration, it is really hard for you to learn how to, how to play Minecraft, you know? We do have results leveraging domain knowledge, like things like LLMs that actually have a lot of domain knowledge from the get-go, so that we can design type abstractions, but this is not something that I will talk about today. But then another thing that I find interesting is to ask from a first principles perspective, are there pieces missing in this full agent architecture, let's put it this way? Well, and there are a couple, right? Like, we're not using options for credit assignment. If you notice what I've been telling you about, it's just like, well, I'm going to select this action to do random exploration. And then at least I know what it's going to happen, is that it's going to be for an extended period of time, and it's not going to just be for one step. I'm utterly ignoring the rewards here. Should we ignore the rewards? Like, when we get to the key and you get 100 points, maybe that should matter, you know? What about partial observability? Can we combine options without additional learning? I was telling you about using this analogy about making tea if you know how to make coffee, but at the same time, right now, we still have to learn value functions for all those things. You know? Can we do model-based reinforcement learning and planning? So my group has been working on all sorts of on all these different questions. Or we have some papers written on this that are either in archive or are published. But I want to wrap up talking about very briefly about these two different results that are relatively recent here. How we can use options for credit assignment, and whether we should define state similarities in terms of rewards as well. Okay? So The obvious question here is, what if we used options not only for exploration, but also for credit assignment? What I mean by that is that we're going to not only learn the options and then call them in an epsilon greedy step, but we're also going to learn option values. So if we know that this option takes me to the reward, I want to be able to use that option to do reward maximization, like in the argmax of my Q function. And when we do this, these are results in the tabular case, but when we do this in the tabular case at least, and we assume that, okay, these are the options these are the eigen options, we're going to compute them in advance, what we can show is that being value aware actually drastically accelerates learning. I can notice those gaps are big. This is not using options. This is what I had shown you before, which is CEO without this value aware, and would be the value aware CEO. And again, in the spirit of continual learning, we can see a lot of benefits by doing this as the world keeps changing. Okay. So that's one thing that I think it's really exciting. It's a direction that's worth pursuing. And the other one is this notion of how do we make those representations aware of the reward? Like instead of just talking about this, maybe true states should be closing time if they lead to similar outcomes. But the similar outcome maybe shouldn't be just state visitation, but also reward. And then let's consider a couple of these environments. And in this case, this red, the agent starts in the blue region. The agent needs to go to the green tile here. But these red regions are not going to be walls. They're going to be lava. Okay, so it's like the floor is lava, and you have negative reward. And then what the agent needs to do is to learn how to solve this task. Everything that I told you so far, this is what the eigenvectors would look like. So maybe this one is the one that we already talked about. Look, that this is not a wall, so it's not that you see a patch here. You just see this very natural thing of going from one corner to the other of the environment. But there's this attraction point here because it's actually the goal state. So that's what the success representation looks like. And it's again capturing this very notion of diffusion. Look, this is the place that it's hard. Like this is one end. And then you can follow along here, and then you can see that it keeps getting brighter and brighter and brighter and so on, right? But now if we were to use this thing that is called the before representation, which comes from the linear MDP formalism, which has some very interesting ties with the maximum entropy reinforcement learning framework. This is what the eigenvectors that we get. So you can see that the eigenvector is literally seeing this reward as maybe a wall, or at least a state that's very bad to get to. Because you get negative rewards, like for here, like again, why would you want to go here? And what is interesting about that is that the moment that we look at what are the options that are induced here, well, initially the thing that I was telling you for most of the talk, well, we're just going to be oblivious to the reward function because literally we are not even seeing it, right? But what we see here is that like here we are able to go around this regions of negative reward, which one feels much more natural to us, and two, it kind of starts to capture this trade-off between exploration and safety, right? Like we want our agents to explore, but somewhat we don't want our agents to do dumb things that we can actually at least tell them that those things are dumb. Okay. So, and then what is interesting here is that we have this trade-off. The red thing is what I was showing you before, that is not aware of the reward. But then this green thing is this new algorithm called Embrace. So what we can see is that the more you are to the right in this first row here, the more states you visited. And you can see that we are visiting as pretty much as many states in many of the environments, or a lot of states, compared to the one that it's just ignoring the rewards. Like it is expected that we're going to visit fewer states because, of course, we're afraid of the negative reward. But what is interesting is that when we look at the reward that we accumulate way more reward than the other one because, again, we're not being dumb. And this is reflected once the moment that we learn how to actually solve tasks. Okay? So, to wrap up, I'm still very excited about options. Like despite all the buzz and the excitement there is about machine learning, about all sorts of other things, I'm still very excited about options. I still think that our agents, they need to better be able to develop temporal abstractions. And I think that we now have option discovery methods that are general, that work, and that demonstrate a virtuous cycle of improvement, are fully experiential, are scalable, are amenable to function approximation, work for different data streams. they don't make any assumptions about the topology of the environment. It's not that I'm looking for bottlenecks, because maybe bottlenecks don't exist in that environment. And they are sort of biologically plausible if you're into that sort of thing. I'm actually giving a talk in a couple of weeks exactly about this. And I know that Ida talked with you about the success representation and how it's related to things we see in the brain and the human behavior. But unfortunately, I don't have time to go in depth here in some of those connections. Okay, but there are some deep connections here to the hippocampus and rhinal cortex and so on. Now, I think, this is my personal opinion, temporal abstraction should be a central piece of reinforcement learning. And the thing that I'm trying to convince you here is that the representations, that option should come from specific representations that are learned by the agent. And then I think it's interesting because this has been a point of view that I have been advocating for almost a decade now. But now I think that's sometimes it's even being taken for granted. People, well, of course, that's how you're going to learn options. And from what I know, for example, a lot of the work that Amy Zhang has on a higher reinforcement that she talked about, it's actually leveraging exactly the same notion. So it just shows how there is this serendipity, and this seems to suggest it's actually a good idea. Because I think that a lot of the work that Amy does is very exciting as well. And I think that given the right discovery method, options are scalable. And I think that when I think about the future and what we should be doing, I think that we should be thinking more about the non-stationarity of the world and trying to do things like in the continual learning setting. I think that this is the future of our field, and I just showed you that having this notion of skills that you can reuse when the world changes, it feels very natural to me, and it's something that we should be exploiting more. Okay? So I think that, so to conclude, this is something that I wrote in one of my papers, and I still believe on that, both because of our ability to do faster path assignment, exploration, to the biological plausibility, and so on. But I think that state abstraction and pure abstraction should be deeply intertwined, where representations and options are constantly refined based on each other. And I still think that things like the successful representation, the Laplacian-based representations, are a key component of this lesson. Okay, so that's it. Thank you very much for your attention. If you have any questions, I'm happy to take them.
Thank you very much, Professor, for a great presentation. And thank you for going through our course and connecting different parts. It really means a lot to us. Thank you. So we are open to questions. So if you want to ask questions, please raise your hand.
Hello.
Hi.
Thank you for your great talk. I have this broad question about the comparison between model-based RL and successor representation. Do you think it? Do you think that any of these, for example, option discovery that you discussed with successor representation, can be done with model-based RL, or do you think that are there any specific features or are there any specific properties or benefits of successor representation that cannot be done with model-based RL, or trying to learn the whole model of the world compared to just the successor features?
Yeah, I think that this is a great question. Like, I think that it has a couple of layers that we can try to peel here. One is that, and I suspect that Ida talked a lot about this in her talk. I don't know if you attended her talk, but like the notion is that like the success representation is something that kind of sits in between the model-free and the model-based RL. So just talking about the success representation, let me tell you why. So I didn't go through this equation in detail here, but when you look at the success representation, you are capturing this notion of how many times do I expect to visit the other states in the future, conditioned by my policy. So at the end, you do kind of have very loose model, let's put it this way, because given the training state, you already know how many times you expect to visit other states. And if you look at this equation here in the matrix form, this is part of the solution to the Bellman equation. If you multiply this by the reward function here, you get the value function. So the success representation, it already captures something about the environment. And what people often say is that it's something in between the model free and model based, because it's something that, well, given a policy, it's kind of a fixed model. It's not that you can say, well, I wonder what, you cannot ask counterfactual questions. I wonder what would have happened if I had done this other thing. But it's already is able to accelerate learning a lot. So there is already a deep connection, you know. Now, when you talk about model-based reinforcement learning, I think that there are a lot of things that we have to think about. Like, are we learning a model? First, to be able to learn a model, then we need to be able to explore. You know, like, so where's this exploration coming from? Maybe it could come from here. Well, how fast do we want our model to be? We can have models that are models that I can actually do rollouts and stuff like that, but maybe I want to have this quick reaction and be able to do something. So maybe the success representation gives you something. Now, from the perspective of the options that I told you about, nothing prevents us from actually using them. So here, what about model-based reinforcement learning and planning? This is a paper that I wrote with Fritz Sutton, I guess 2 years ago now. And it's this paper about reward respecting subtasks. We call it the STOMP paper because we talk about how we are going to define a subtask, we're going to learn an option, we're going to learn a model, and you're going to plan with it. And we just evaluated eigenoptions in this sense, in the set. Basically, like, well, if I have that, I can compute the successful representation if I have the model, and then I can see how well they lead to, how well they when we're trying to plan. You know, so I think that all those questions are. So this is a great question because it touches upon some of the frontier of what we would expect to be dealing with our RL agents, and at the same time, it's a very easy question to answer because. Well, there is a lot of deep connections between these two things, but between these different things. But at the same time, none of them are orthogonal to each other. They all can go well together, you know. Like, and I think that this is one of the exciting directions that we could be looking at. But all that being said, let's not forget that learning models is extremely hard, and I think that this is what keeps holding us back. Is that we still struggle to learn models that are, or like. We don't know how to learn models that are perfect. Almost by definition, they cannot be. But then we don't know how to plan with imperfect models. So we keep being stuck in this conundrum on how we do model-based reinforcement learning as effectively as we do, let's say, model-free reinforcement learning.
Thank you. Just because one of the disadvantages of successor features that I've seen being mentioned a lot of places, it's always given a policy. So it's
yes.
Is that right? So it depends on the policy, and when you learn the model, you can use it with any policy. But the successor feature that you learn, it depends on the policy. So I'm really interested to know about the trade-off that we have here. Okay, that we put a lot of computations to learning the representation, but we are limited to one policy, and what else could we have done with the computation that we have about in regards to learning the model and try to do some kind of exploration with that? For example, doing with epistemic uncertainty and try to for example, in the case of some of your examples, to see that okay, we have this model that doesn't know the states, that in some states it doesn't have very high confidence. So that's the places that we tell the model to go and explore further. I think yeah, that's the trade-off that I wanted to see. What are we giving and what are we getting instead?
So I think this is a great question, and this is, I think, that something that, well, I mean, the way that I like to put it is that I don't think that the success representation being policy dependent is a bug. It's actually a feature, and let me tell you why. Because let's say that I consider the uniform random policy. Okay. Now we can consider the uniform random policy either because we're actually being random or because we are doing important sampling to correct to that and get the uniform random policy. That it's much easier to do that for the uniform random policy with important sampling than any other policy that we don't have support, right? The moment that we do this, if you think about the induced dynamics of the MDP, that is going to be a function of your policy, how you behave, and the transition dynamics, right? Now, if I put equal weight to the policy, the way I behave, what I'm actually doing is that I'm marginalizing out the policy, and I'm just getting the dynamics of the environment. So if I want to use the random walk, it's not that I'm actually limited to the random walk. I'm literally marginalizing out the impact of the policy because I'm saying, well, I'm going to put equal weights to every action that the agent might take, which means that I'm ignoring the action, and I'm actually going to just look at the dynamics of the environment, you know? But now, let's say that you don't want to ignore an action because maybe you are concerned about safety. Maybe you don't want to go into lava. Maybe you know that the agent is going to 90% of the time work on that direction. Then you are not constrained to the uniform random policy. You actually have a mechanism of incorporating the way you behave into that. You know, like, so, I mean, I don't think that you are losing anything by having this, because I think that you just have to think carefully about how you leverage this policy formulation. But I agree with you that I think that there are interesting questions about modeling uncertainty, even when we want to talk about exploration, right? Like I have one of my students is looking at this. If I'm going to visit a place, how do I make sure, like, how do I distinguish between aleatoric uncertainty and epistemic uncertainty? What are the things that are actually reducible when I'm doing exploration and that type of stuff? And I think that these are all excellent questions. But yeah.
Thank you again for your great talk.
Thank you for the question. Any other final questions, burning questions, or are we done?
I can't see any other question.
Yeah. That's great then. Thank you so much for having me.
Thank you so much. Just for a closing question, can I ask for your advice for the researchers who wants to start their research career in the 2025 and just want to go and do something cool in the reinforcement learning?
Yeah, that's a very exciting perspective. Cool. Okay then.
Yeah.
So we'll
No. Sorry, I asked.
So do you
what is your advice? Sorry, I asked. Sorry.
I thought for you specifically. What is my advice for what? Sorry.
Yes. Sorry. I didn't frame my question very well. I asked, what is your advice for the students who just want to start a research career and go do something cool in the reinforcement learning? Wants to start, how do they found a good idea to work on? How do they approach it? How to go about doing it?
So I guess I have 3 advices. Let's see if I can go over them before I forget the third one. One is that do research for the right reasons. What I see now is that I think that a lot of people, I see them doing research for the wrong reasons. Oh, I want to do research. I want to do a PhD because I want to work at company X, or I want to do a PhD because I want to work on this particular project. And I think that this is horrible. And the reason this is horrible is because you don't control the future. So by the end that you finish your PhD, maybe you really wanted to do LLMs, and then no one is doing LLMs anymore. And now you just look and say, well, what do I do now? It's just like, oh, we were doing research for the wrong reasons. You know, like, so you should be doing research for the scientific curiosity and like to just get a joy of this, and not so much because, oh, I want to work in this particular company or something like that. The second advice that I have is that don't do research based on, research is not a popularity contest. Now, there are areas that are extremely popular, and there are areas that are not popular. And it's very easy for you to pick areas that are the popular ones. Well, that's what everyone is talking about, and that's what I should do. And like, And there is a reason they're popular. They are actually very exciting. So by no means it's wrong to work on those areas. But at the same time, I think that some people think that this is the only thing that exists. And I think that you should know that whatever you choose to work on is because you actually care about that and you believe in that, and not just because someone else told so. Mainly because with AI, there's so much money now that every area and every research question and every project is clouded by PR machines. So now it's all about like advertisement and about propaganda, and how much of that actually you can figure out, which is interesting and what you think has a future. And the third one, it's the more concrete one. It's hard for me to say, well, work on X or work on Y, or like this is how you should apply research. But I think that one very low level advice that I give to my students that I think helps every time that they're trying to look for a project or something like that is, well, first, of course, you have to read a lot to know what's out there in the field. But after you read, let's say that you find a paper that you really like. Oh, this is so cool. I would love to have written this paper. Trying to reproduce it. And the moment that you're trying to reproduce that paper, and you're actually trying to get it to work, to match the graphs in the paper, what you're going to see is that quite often, almost all the time, it's not that easy. And it's not because the authors are doing a bad job at explaining or anything like that. It's just like there's so many details that sometimes it just takes for granted. Sometimes, like I can't explain to someone how to do automatic differentiation in JAX to be able when I write my paper. Like so, it gets to a point that you just assume that there's some level of understanding. And of course, authors often fail at giving out the details as well. So, but now the moment that you go through this process and you do that, what happens is that you will fully understand that setup, and very, very, very likely you're going to say that I don't like this piece. Oh, this is kind of brittle, or this is inelegant, or oh wait, it was so hard to make this work, or this doesn't work at all. I have to press it with my left hand because if I press with my right hand, it doesn't work. That's how brittle it is. So that's the moment that, well, maybe I want to fix that aspect. Like maybe I want to ask that the question because maybe the planning component is the one that doesn't work, or maybe I realize that I have to have a very accurate model, and if I ran it for a little bit shorter, my model was not accurate enough. So now maybe I want to try to, and that's a great way of trying to find concrete research questions for you to start working on. And the moment that you start dabbling your feet on the water, it becomes easier to abstract that away, and you start to ask bigger questions that are like further away from the papers that you've read. So yeah.
Thank you. They are great advice. Thank you. And I think with them, we can finish up the session. Thank you so much again for accepting our invitation and taking the time to going to our course and connecting different parts of it. It really means a lot to us. And thank you again. And I'm very grateful to have you with us.
Of course. Thank you so much for having me. It was a pleasure.
Thank you. Have a good rest of today.
Have a good night.